So let's start by solving today's quiz. Okay, this was a quite simple question, but it combines two things we have actually learned throughout the course. First is energy conservation, the other is projectile motion, right? So what does the question ask us to calculate? It asks us to calculate how far from the edge of the semicircle does this particle fall. So the motion of the particle has two distinct parts. In the first part, the particle will follow the track. It will go through this semicircular track. And then it will actually reach to the top of the semicircle with some velocity. Let's call this Vt, Vtop. Okay. What's the easiest way to calculate this velocity? During the motion, energy is conserved, right? So first, let's calculate Vt. And here I will use energy conservation. So what's my initial energy? If I choose my potential energy reference level to be the initial or the flat part of the track, then initially, do I have any potential energy? There is no potential energy. All the mechanical energy is the kinetic energy of the particle. So my initial energy will be 1/2 m vi square. How about the final energy? Well, final energy, let's call this E top energy at the top. Kinetic energy part is 1/2 m v top square. But now I also have potential energy. What's the amount of potential energy? The height from my reference level is 2 times r. So it's going to be m times g times 2r. So let's equate these two. 1/2 m vi square is 1/2 m vt square plus mg 2r. M's cancel. So Vt square is Vi square minus 4gr. And I've been given that Vi is, or Vi square is 5 times gr. So I can say this is 5 times gr. So this is going to be just gr. Vt will be square root of g times r. Now, second part of the problem is just the projectile motion of this particle. Okay. Do I know its initial velocity? Yes. So this is projectile motion with initial height 2r and initial horizontal velocity square root of gr. So if this is my x-axis, this is my y-axis, my initial position is 2r along y, and my initial velocity is square root of gr in the positive x sense, the way I drawn the axes. So what will the dependence of x on time be? This is just going to be motion with constant velocity. So it's going to be square root of gr times t. How about y of t? Well, I have an initial value 2r, right? At time t equals to 0, I'm at 2r. Do I have any initial velocity in the y-axis? No, I don't have any initial velocity. So I only have the acceleration term, 1/2 g t square. What would I like to calculate? I would like to calculate the x coordinate, which I call d, when y is 0. So find the time of flight is y at tf is 0. So it's going to be 2r minus 1/2 g time of flight square 4r over g square root would be my time of flight, which means the distance d which was asked is x coordinate at that time. So it's going to be square root of gr times tf square root of 4r over g. G is cancelled. I just find a result of 2r. Did I reach my goal? Yes, I did reach my goal. Okay. And what's really interesting is I don't even need to know g or m. Okay. So which is kind of interesting in this problem. Why does this result not depend on g? Okay, maybe let's look at the units. There is nothing. So I reached my goal. The units are obviously fine. D is meters, R is meters, so units are fine. How about the limits? Here, you would expect if G is large, right, then it will be harder to get to the top of the semicircle, and you will fall down faster, right? But the question is a little bit tricky. It's giving you an initial velocity which scales with g, which increases with g. That's why, I mean, whoever has prepared this question made sure that g is cancelled. So it's not some physical effect. It's just that because your initial velocity increases with g, that cancels the effect of g on d. All right? How many of you found the result, the 2r result? Okay, good. So, any questions about energy conservation at all? So, we've learned about work energy theorem. We've learned about kinetic energy. Then we've said forces can be either conservative or non-conservative. Conservative forces could be defined in terms of some potential energy. So we modified our work energy theorem saying that it's not the change in kinetic energy, it's the change in total mechanical energy equal to work done by non-conservative forces. Okay? And then this was a wonderful tool. If mechanical energy is conserved, or if I can actually calculate the work done by non-conservative forces easily, then I basically just care about the initial situation and final situation. So that was the power of energy conservation, right? I don't really care what happens in the middle, right? So it helps me solve problems more easily if I'm interested only in the final quantities. But if I want to find the path the particle takes between the initial time and final time, or any questions about time, how long would it take to get from one point to the other, those cannot be answered by energy considerations alone. All right? So there is a trade-off. You maybe solve some problems more easily, but it's not as powerful as finding the dynamics. Nonetheless, you'll see that conserved quantities play a very important role in physics. Okay. Our understanding of physics right now is mostly based on our understanding of symmetry and conserved quantities. Okay. For example, Einstein's theory of relativity, you're not going to study it in Physics 101. But it basically makes a very interesting statement. It says speed of light is the same for all observers regardless of their velocity. So that's sort of a statement of symmetry. So you change your system, but a variable doesn't change. Okay. That creates a lot of interesting consequences. Okay. Or we'll see in Physics 102 that there is a quantity called electric charge in the universe, and that's a conserved quantity. Electric charge being conserved has a lot of consequences, some of which we'll actually study in Physics 102. But let me make a parallel. And where do these conserved quantities come from? For energy conservation, I said, hey, it's, anytime it's not conserved, we invent new potential and add it to the energy conservation law. Maybe that's a little bit unfair, because right now we believe, as far as our experiments show us, all the forces in nature come from 4 basic interactions, 4 basic forces, right? Now, let me also make a parallel. And how do you get other conserved quantities? Do you know why the topic of this year's Physics Nobel Prize? It's quantum mechanics, but it's use of topology in quantum mechanics. Okay, topology is the branch of mathematics which studies conserved quantities, if you want. Okay, under geometry, some geometric properties which cannot be changed easily. Okay, for example, if you have a plane with a hole in the middle, no matter how much you bend your plane, the hole will still be there. If you look at how many holes this plane has, bending it and stretching it doesn't change the number of holes. So that's a conserved quantity. So the idea of conserved quantities is extremely important in mathematics and physics. And we now understand some of the conserved quantities in nature have this topological origin. So that was sort of the reason for 2016's Nobel Prize. Now, what conserved quantities have we learned up to now? We've only learned energy. Okay. Hopefully, today we're going to study another conserved quantity, momentum. And before Physics 101 is over, we'll study one more conserved quantity called angular momentum. But those are not the only conservation laws in nature. Okay. We'll talk about electric charge being a conserved quantity. And then there are other conserved quantities which are a lot of you are in physics department, so maybe you'll see them before you graduate. Things like lepton number conservation and other symmetries of nature. Okay? So let me define momentum. I've sort of raised your expectations saying that this is very important. There is a Nobel Prize for conserved quantities, so you're all listening, thinking I'm going to tell you a great secret of nature. But I'll actually give a very mundane definition. You already know. The momentum of a mass m moving with velocity v is m times v. And I'm sure when you've learned about this concept for the first time, you really said, hey, I mean, these physicists are crazy people. I mean, they define mass, they define velocity. These are two things. Then they multiply it and call it something else. So why do we ever need to define such a concept? Now, here is the thing. Let's look at time derivative of momentum. So I would like to calculate d by dt p. By the way, of course, momentum is a vector because it's a scalar times the vector velocity. And what should be the unit? Well, clearly, it should be kilogram meters per second. Thankfully, it doesn't get a name. We don't call it Ahmet or Mehmet or something. Okay, kilogram meters per second. So if I take the derivative of momentum, mass is a constant. So I have dv dt. But what's dv dt? A, acceleration. But what's m times a? Newton's second law tells me F. So maybe I can rewrite Newton's second law as saying dp dt is F. So force is the change in momentum. And why is this useful? I will claim that this is actually a little bit more general than F equals ma. This relation holds if not only v, but also m is changing with time. You may say, hey, why should I care about, for which system does m change? And let me give you a very simple example. If you have a fluid, let's say you have a hose, garden hose, and you're watering your garden. So you're throwing mass of water towards your flowers. You'll feel some back reaction. You'll feel a reaction force. And that actually is not the velocity of water going from your hose is not changing in time, but the mass through your the mass passing through your hose is changing. So that's why you actually feel that force. So the definition of momentum is good, at least for those systems, for the systems where mass of an object is changing with time. Okay? I have to be more careful, and I'll define it more carefully. We'll look at these systems when we study rockets. Okay? But I'll also claim that this equation, so we have looked at Newton's second law that gave us dp dt is F. Newton's first law is kind of trivial, right? If F is 0, dp dt is 0. But if I look at a more general system, let's say that I have two masses, m1 and m2. And let's say that at any moment, this guy has v1, this guy has v2. Now, if I look at the system, let me assume that there are no external forces on the system. Okay? So maybe I took these particles to outer space, very far away from all stars, planets, and they have initial velocities. Now, in general, it's very hard to characterize all kinds of forces these two objects are going to apply on each other. Right? If these are simple masses with no electric charge, they will only actually interact when they hit each other, right? So that's the, if they collide, like if you have small planets. But what happens if they are electrically charged particles? They will actually start pushing each other from far away. There will be gravitational pull even if they are small planets, right? That may be small, but there will be some gravitational pull. What if they actually have some magnetic moments? There will also be magnetic forces between these two objects, right? So in general, interactions are hard to characterize. I can write F equals ma if I can know how F depends on their separation and other things. But here is one thing I'm really sure of about these interactions. Whatever force the second particle is acting on first one, an equal and opposite force is acted by the first particle on the second particle. Right? And Newton's third law tells me that F21 as a vector is just minus F12. So this is Newton's third law. Well, you may say, okay, so that's nothing new. You've told us this a month ago. But now look at the following. Let me look at the quantity, which I'll call capital P, which is the momentum of the first one plus momentum of the second particle. So it's going to be m1 v1 plus m2 v2. And let me take a time derivative of this total momentum. It's going to be dp1 dt plus dp2 dt. But I reformulated Newton's second law, so I actually know what dp1 dt is. This is F1, or what I called F2 acting on 1. And this guy is F1 acting on 2. So this is going to be F21 plus F12. Wow. Well, the second term is just the negative of the first one. So it gives me 0. So this is pretty powerful. As long as Newton's third law applies, and we know that it applies everywhere, right? The total momentum of two particles cannot change due to interactions of these particles with each other. So one thing that's really important in this assumption is that we think that this is a closed system. Closed system means there are no external forces or no external net forces on the system. Okay? Well, this is really powerful. This is great. Momentum, or maybe let me rewrite this in another color now. Total momentum of a closed system of particles is conserved. And what I meant by closed system was no net external force. This is actually a very powerful statement. Maybe it's actually better than Newton's third law. It's actually more general than Newton's third law, especially when you study not only classical mechanics, but relativity and also quantum mechanics. Conservation of momentum holds beyond classical mechanics, beyond Newton's equations. So maybe we should say the conservation of momentum is the root of Newton's third law. So we actually understand Newton's third law better. Action equals reaction because total momentum has to be conserved. Although I did the derivation sort of in reverse. All right? Now, why is this useful? It's useful because if I have an isolated system, I don't actually have to know the kind of interactions the system has to predict some of the final quantities. Okay. Let's solve an example. Let's say that I have a frictionless plane and I have a particle of mass m and another particle of mass small m, and initially this mass m is going with some velocity v0. To make things interesting, I'll put some glue onto the first mass. Okay? So when these objects collide, they will stick to each other. And what I would like to find out is what's the final speed, final velocity of the combined system. Now, if I did not know about concept of momentum, this is not an easy problem to solve. Why? Because what I actually have to do is I have to write the forces acted by the big mass on the small mass during collision. Furthermore, I have to take into account that there is a glue between these two objects, right? So they cannot separate from each other during this collision. It's a big mess. It's not easy. Engineers who study collisions, they run big computer codes to figure out what goes on during a collision. But the nice thing about momentum conservation is I don't have to know what really goes on during the collision. Okay? There is something complicated going on. But whatever happens, those forces acted by the small mass on the large mass are equal and opposite to forces acted by the large mass on the small mass. So if I look at total momentum, the total momentum of the system must be conserved, right? So the only thing I need to say is that this is a closed system. Why do I say, are there no external forces on the system? There are external forces, but whatever mg, the first mass fields will be cancelled by the normal force. Similarly, small mg will be cancelled by the normal force acting on that. So the net force on the system is exactly 0. So it's a closed system. If I have a closed system, then momentum is conserved. What's my initial momentum? Initial momentum is m times v0 plus small m times 0. So it's mv0 to the right. How about my final momentum? Well, final momentum, big mass and small mass are moving together with velocity v1. So it's going to be m plus m v1 to the right. If momentum is conserved, capital M v0 must be capital M plus small m v1. I was asked to find v1, which is going to be m divided by m plus small m times v0. Does it make sense? It makes sense if that mass, if I'm hitting a mass, I expect the system to slow down. It does slow down. v1 is less than v0. And if the mass I'm hitting is larger, it will slow down more, right? So it's also intuitively correct. Now, let me define one more quantity. Okay. So how does the momentum of any object change? Well, now I'm actually writing dp dt as my f. So let me do something which is going to, and do not show this to your calculus professor. He or she will be very angry. I'll say, hey, dp is f times dt. Okay. You're not supposed to be able to do that for differentials. Okay. But in physics, we believe that all these derivatives can be replaced by deltas, small changes, right? So I can treat them as numbers. But now I will do integration. And I'll say, so some initial time to final time, P final minus P initial. So the change in momentum of a system is, if there's a changing force on the system, the time integral of the force. So this is sort of similar to the work energy theorem. What did we say? We said the change in energy is work done. Work done was integral of f over x, right? Integral f dot dl, right? So here similarly we say the change in momentum is the integral of the force over time, right? So this new object gets a name. It's called the impulse. Now, why is impulse important? Or, well, let's solve a very simple question. Using this impulse, we can look at all these violent events like collisions and other things. At least characterize the forces during such a collision. So let me solve some examples. Let's say m equals 1,000 kilogram car hits a wall with v equals 10 meters per second. The collision with the wall ends in 0.01 seconds. So from 10 meters per second to 0 meters per second, the car goes in 0.01 seconds. Find the average force the wall acts on the car during collision. So, in the initial case, I have a wall here, and I have my car going with velocity v, and it has a mass m. And when the collision is over, velocity of the car is 0. So what's my initial momentum? My initial momentum is m times v. And my final momentum is 0. Right? So delta p, let's just look at the magnitude, is I've lost m times v of momentum. And that must be f of t dt during the collision. But what am I asked to find? I'm asked to find the average force. What does that mean? What's the average force during the collision? Well, it's going to be, this integral is going to be f average times delta t, right? Because average force, the time average would be f dt divided by delta t. So it's going to be mv. So the average force is m times v divided by delta t. If I actually put in numbers, I said this is 1,000 kilograms, v was 10 meters per second, and delta t was 0.01 seconds. So this is going to be 10 to the 4, 10 to the 6 newtons, a million newtons. The numbers are not, and this is a fairly low speed collision. The numbers are not super accurate, but they are within the order of magnitude. So that's a huge force. That's why car crashes are actually very dangerous. The force, whatever object is applying on the car, and the car applies a fraction of that force onto your body, it's very dangerous. How can you make it less dangerous? Let's look at the formula. Obviously, the best thing is not to crash the car, but if you're going to crash it, try to crash it with low velocity. Obviously, low velocity crashes is going to damage you less. But there's another thing, delta t. Collision time, you would like to increase as much as possible. So what does the seat belt do? The seat belt actually increases your collision time with the car. You start colliding as soon as the seat belt is acting on you. That becomes a part of the collision. So you basically actually, even if the car stops within a millisecond or within 10 milliseconds, you actually take 5 times that amount to hit the steering wheel. So that when delta t is 5 times larger, the force is going to be 5 times smaller. And you know, in the 1960s, 70s, car manufacturers were trying to make stronger and stronger cars with steel frames and other things. That was very good for the car. When you hit the car was not damaged, but the driver was killed. Okay, why? Because I mean, it's a steel car. It didn't actually, the collision time was very small. It remained, well, basically, the car stopped and it stopped you very fast. Nowadays, cars are purposefully built to increase this collision time. There will be structures which are crumpling so that it takes a time for you to slow down. It actually increases the collision time. All right? Let me remind you, no classes next week. I'll see you in 10 days.